Dempster-Shafer inference is the last framework and last technique we are going to deal with in this presentation, at least in this first part of the presentation, and has the Bayesian inference provide a framework for combining different sources of evidence into a global belief for a given hypothesis. So Dempster-Shafer inference can be seen as an extension of the Bayesian inference with respect to our target, our decision fusion target. So what is the main problem with Bayesian inference? The main problem actually is operative. As we see, Bayesian network holds on the construction of a belief function, which is a posteriori probability. In order to compute the posteriori, we need to compute the likelihood, and in some cases we need also the priori probabilities. So in the reality, these, especially the likelihood, is absolutely difficult to have. We need huge data set, and sometimes we don't have this kind of data set to compute the likelihood for every sensor and every state. For this reason, Dempster-Shafer inference try to overcome this structural deficiency of the Bayesian inference, providing a kind of change of paradigm in the definition of the probability function. More specifically, in the Dempster-Shafer inference, we can model what we call the uncertainty. So more specifically, we can assigning a probability value to that the system is in none of the states or in more than one state. And doing this, Dempster-Shafer inference theory provide a simple way to combine different sources of information. So this is the main difference, this is the introduction to this technique. Let's go now on the definition of what we call the mass probability function. So as we know, probability function is defined as a function from a set omega, which contain all the states, to the interval 0, 1. This is at least in the Bayesian approach. In Dempster-Shafer, the domain, or what we call the mass function at this point, is not the omega, but is the power of omega, which represent all the subset of the omega set. So basically, we define a function from all this subset to the 0, 1 interval. And the constraint, of course, is the fact that the sum of that all the masses function is equal to 1.
So, given the complexity of this topic, I think that it is worth to go directly to the case study and to the example. For Dempster-Shafer inference, what we use is this paper, which is reported here on the bottom of the slide, which is a sensor fusion application in the sport activity monitoring domain. Specifically, in this paper, they try to use 4 sensors: oxygen saturation blood sensor, an airflow sensor, a thermometer, and a galvanic string response sensor to determine the level of fatigue of an athlete. This level of fatigue is distributed in 5 stages. The state X can have 5 values from the lowest fatigue to the highest fatigue, X5. As you can see here, for each sensor, there is a kind of range assignment with respect to the state. So if our temperature, for example, is between 35 and 37.1 for the thermometer, so for the single sensor, we are in the state X1. But if we go a bit, we zoom a bit on this range assignment, for example, for the thermometer, you will see, and here you have, on the right, you have a better explanation. You will see that this range assignment is not actually strict, but is overlapping. So we have some overlapping region where our athlete, according to this sensor, can be both in state sample or in the state X4. So in this case, we don't output a state, but we output actually a table with the mass function for each of the state and for each subset. So again, here we can have This is just on the table an example, a didactical example that I created, with some random number. Given the fact that our max function from the subset to the 0-1 interval, we can assign even a value to our uncertainty. So the max function, or the state is both x4 and x5, is 0.5, and of course is 0 elsewhere.
Given the max function we defined in the slide before, we are not able to define two main metrics that will be used later to have the proper classification and the best estimation of the final state. So the two metrics are the credibility and the plausibility. So credibility is a lower bound of the confidential interval and represent the sum of all the max functions. Given an hypothesis A, so an hypothesis like the state is x3, or the state is x5, the state is x4 or x5, and so on. The credibility of this hypothesis is the sum of the max function whose evidence support A. So all and only the subset of the hypothesis A. Plausibility instead is a kind of upper bound of the confidence interval and represent all the observations that do not rule out that given proposition, the given hypothesis. So basically all the subset whose interesting set is different from the void set. I provide here a really straightforward example to understand how we can build the belief and the plausibility function given the max function. So let's go back on the example. So let's imagine we measure a temperature of 37.3 degrees, and actually the logic of inside our sensor, we have no idea how this logic works, but tell us that the mass function, we have a certain probability that we are in the state 3, a certain probability we are in the state 5, and another in the state 4, but actually we have some uncertainty regions where we can be in both the two states. So to build the belief function, if you see the belief of x3, x4 is the sum of all the subsets here, and of the mass function of all the subset, and you can see that, for example, the highest in the belief is the subset, the hypothesis x4, x5, which take into account x5, x4, and x4, x5. Instead, the plausibility, for example, for x3, x4 is of course the mass function of x3 and mass function of x4, but we have even to take into account this set, this hypothesis, because x4 and x5 has in common with x3, x4 the state, the hypothesis x4. So we have another term, and you can see that the plausibility in this case is greater than the belief function. So for each of the states, you can see that belief and plausibility give us a lower and an upper bound, and in the next slide we will see how at the very end of the day this can be used to do the proper decision on the value of the state.
The real decision fusion and sensor fusion part happen actually at the end of our explanation on Dempster Shafer theory. So as we said in the previous slide, each of the sensor, in this case on the paper in input, we consider 8 sensor, and each of the sensor given a measurement that they perform, define with a logic inside it a mass function of the state, so which is defined in the way we described on the slide before. The real actually fusion engine, the real fusion part happened at this stage. So Dempster Shafer theory, in the way that
it is built, actually provide a really powerful tool, which is a combination rule. of the hypothesis, and this is described here. So this formula is a way of combining two mass functions over the same set, the same domain, the same input set. So what we do actually, provided all the mass function given by the sensor, is combining through, maybe a more sophisticated version of this rule. And what we had at the very end of the day is actually the same table we described before, so a mass function table, but considering the measurement and the logics of each of the sensors. So we have a table actually, where we have x1, mass of it, x2, mass calculated on this x2, and so on. At this point, what we do actually is calculating the belief function and the plausibility function, the end one. And with our decision logic, we compute what is the hypothesis that maximizes one of the two. Of course, there is a lot of there are a lot of possibilities in this case. We could choose an highest belief criteria or a high plausibility criteria, or we can actually provide a combination of the two. This is not something that the theory covers, it's something beyond the theory itself. The main point is that we have some belief functions that can be maximized. And the state is, of course, the output of this logic block.